question number 2, or rather, this is a continuation of the same one. Now, let's part C, define force. We got to just do this right. We're continuing on from the last one. All right, define force. There's only one way to define force. Force is the rate of change of momentum. There are many ways to sort of correctly think about force. A force is a push or a pull. Force equals mass times acceleration. That's a special case of this. This is the definition of force. Force is the rate of change of momentum. So force equals change in momentum over change in time. That's the definition of force. It says the motion represented in 1.1 is caused by a resultant force acting on the object. Well, yeah, I mean, Newton's laws, you guys, look. This doesn't happen on its own. Things don't just accelerate on their own. Forces cause this. Objects in motion just will remain in motion like this, straight lines, okay? Flat lines, just going at constant velocity. Anytime something changes its velocity, speeding up or slowing down, acceleration, deceleration, we say, well, forces are required to do that. That's really captured with both the first and second law, right? It's like saying the first law says, well, things just kind of go along like this. They maintain their current state of motion until some net force acts upon them. Once that net force acts upon them, they're going to accelerate in the direction of that net force. But you know, the mass has something to do with it too. In other words, for a given force, you push something very massive, it goes a little bit. The same force, push something tiny, it accelerates a lot, right? So the product of these two equals the net force. And, you know, Newton's second law sort of also incorporates, you know, how mass sort of affects that, how inertia, right? So mass is inertia, and the first law is the law of inertia. Objects have a tendency to resist change in motion. The more inert they are, the greater that tendency is. The more massive they are, the greater that tendency is. Moving, wants to keep on moving. If it stops, tends to stay at rest. Some net force acts upon. So it says sketch the variation of F, the force, with time t from t equals 0 to t equals 12 seconds. Numerical values are not required. So this is going to be kind of tricky. We have to look at the variation of force with time, but over all 12 seconds. So let's just kind of think our way through this together. Here we know that a force is causing this. And so there's going to be, you know, but what's the variation of the force? So again, if we think about force equals mass times acceleration, we know that there's an acceleration here. Okay. This is of an object. The variation with time t of an object, right? They don't really tell us anything about the object, but let's just say, well, its mass isn't changing. They're showing us how its velocity is changing. They don't say anything about the mass. So if we have a constant acceleration, right? There's one value of acceleration. Its velocity is the thing that's changing, but this is a constant slope, right? The slope isn't changing. So there must be a constant force. So keep that in mind, that over the first 4 seconds, we'll have a constant force. In other words, force against time is just going to look like this, a flat line. Like whatever that force is, it says numerical values are not required. If they gave us the mass, we'd be able to calculate, right? We know the acceleration. If we want to, we just say, like, we'll make it a convenient number, make it 1 kilogram. Then the 0.175 meters per second squared of acceleration times 1 kilogram equals, you know, 0.175 newtons. That would be the net force that's causing that 1 kilogram object to accelerate at that amount. So for the first 4 seconds, there's a non-zero net force that is constant, right? It's causing this acceleration. And then at 4 seconds, what happens to the acceleration? Again, we have to sort of use the velocity time graph to deduce what the acceleration is, and then use Newton's second law to figure out what the force is doing. So from 4 to 8 seconds, so these are, you know, from 0 to 4, there's a non-zero force plotted against time. We'll go translate this onto the other graph in a moment. From 4 to 8 seconds, what happens? Drops down to 0. If there's 0 acceleration, that means the net force is 0. Right, 0 equals, doesn't, you know, 1 kilogram times 0 is 0 net force, and so it's going to kind of drop down to 0. Okay, for 4 seconds. So from 4 to 8 seconds. And then here, there's a force causing deceleration, right? So again, there's a constant slope here. If we wanted to, we could calculate what the value of the slope is, how steep of a drop it is, and that would give us the deceleration. So it's gonna be a negative acceleration. So just like acceleration, the vector, this whole question started out with the difference between vectors and scalars. Well, now we're gonna be mindful of a negative acceleration is gonna be caused by a negative force. In other words, whatever force was speeding this thing up was acting in a certain direction. The force that's going to slow it down is going to act in the opposite direction. So it could be brakes, it could be a vehicle that's sped up, it could be a person running that slows down, hitting the brake one way or another. And if you look at the graph, you see how our y-axis is scaled in such a way that we can put negative values on that. So at 8 seconds, from 8 to 12 seconds, it's again like this. There's a constant force. And maybe what we need to do is just compare it to the first one. So maybe we should calculate what it says. Numerical values are not required. In other words, we don't have to but we should be able to just sort of say, well, upon inspection, it looks to me like this is steeper. And in fact, you can prove to yourself that it must be, because here's the same time, 4 seconds, and we're going from like this speed to here over the same 4 seconds, the same time period, 4 seconds. We go from that top speed all the way down to 0. We don't stop at this. If this point went to there, then the steepness would be the same as that. So this thing has a sharper drop. It decelerates more rapidly than it accelerates, right? So in other words, the force that's causing this deceleration must be greater than the force that caused this acceleration initially. So we just want to kind of show that relatively true. However high we draw this force, we know it drops to 0 from 4 to 8 seconds, and then it drops, further than this initial accelerated force, right? There's the decelerated force that's going to be, also constant. So it still gets a flat line. It's a constant force. The force doesn't change, okay, but it's not negative. So I would draw something like one, two, three, 4. So if I go up 5 squares here, there's my sort of non-zero force, and then it smashes to 0 to there. And then if I go down 1, 2, 3, 4, 5. And like that. That little staircase right there is a good answer, but you could have, chosen a slightly different way to represent that, but I think that's good, right? So as long as you've got, 0 force when it's not accelerating, you got a positive force initially, and then this one should sort of drop further negative than the first one. You know that it will take a greater force to decelerate it, change its velocity over the same 4 seconds, or over the equivalent sort of 4-second time interval. Now that I think does conclude the first question, which really folded in some dynamics with the kinematics, right? So kinematics, study of motion without regard for what's causing that motion or changes in the motion. But forces cause changes in motion, acceleration. So we consider that as well.